Hi, I'm Gary, and I want to show you how I use Cloudy. So I want to talk about a way I get a lot of predictions out of Cloudy. It's a facility I use all the time. When you run a model, you may be interested in only half a dozen of the lines it predicts, and frequently you run it as a grid command, so you're varying parameters. And you want to extract only a tiny fraction of the predictions that are in the model. It's overwhelming at first. So the save line list command, the family of commands, is described in this part of Hazy, and it's the way I use to extract predictions and get them into a publishable form. So the idea here is you set up a grid run where you've running many parameters, and you want to extract, say, the brightness of 5007, the O3 line, as a function of other parameters. So you set up a line list. It's a file that specifies a list of all the emission lines you want to save. So it's a data file. And then this save line list command takes that list of lines and looks up all the line predictions for every model that you run. And then it reports this in an output file. So we'll see examples of three main options that are used with this command. And we'll see examples of the line list files that result. Now, the nuisance in this is that Cloudy has to specify each line uniquely. And we specify emission lines. It wasn't our idea. It was the 19th century atomic physicists. You have a species label like H1 or carbon 4 or H2O, and then you have a wavelength. So together, those uniquely specify a line. So you have to get them both perfect. So the label is usually 4 characters long. So carbon 4 would be C space space 4. Longer labels are put inside quotes, and frequently for complex molecules, you'll have a species in a quote. Then the wavelength has to be reproduced to the wavelength that Cloudy expects, because there's often many lines very close to each other. You need to figure out which one you want. Now, instead of trying to memorize all that, we have a series of line list files that are in the data directory. They all start with line list. Each one of these line lists was curated for a different purpose. So line list BLR is for the broad emission line region in quasars. HII, that's for H2 region, like the H plus layer and M16. So there are other files here. The files contain just lists of emission lines, several hundred of them. They're sorted by wavelength. So if you know you're after H beta, you could pick out any one of these, go down the file to 4861 roughly, see exactly what Cloudy is calling it. There's a comment at the end of the line. You can make sure you've got the right line, and you copy paste the emission lines into the file that you're actually going to use, the data file that specifies your lines. This is an example of a data file. It's in the share for these YouTube videos under this lecture number. It's called linelist.dat. And so the way I would use this is open one of these master line lists, pluck out the 6 or 8 lines I'm very interested in, and then paste them into this kind of a data file. And so here's a list of lines. The sharp sign is a comment. And we have a couple of strong hydrogen lines and O3 lines, a couple of sulfur 2 lines, and nitrogen 2 crept in here. So these are important diagnostics for temperature or for density in many regions. So what you would do if you do save line list, you have to have a format. And the way to think of this is algebraically. So the format of the command would be save line list. And then this is the specification of which lines you want. And then Cloudy is the atomic physics engine that changes this list of line lists into actual physical quantities like a luminosity or an intensity. So you can view this as algebraically A equals B. So B is the specification of the lines you're interested in. A is the predictions that come out. So the lines tabulated in the second file will be saved in the first file. If you don't have any options, there are 2 optional keywords here that's not shown here. The units will be relative intensity. So that would be the intensity of a specific line divided by the intensity of a normalization line, which by default is the H beta line in the optical. So it's a dimensionless number. And so for the example we just saw, these are the predictions for the smoke test. And you see, this is H beta 4861. It's the relative intensity, so it's relative to H beta, so it is 1. H alpha is a couple times H beta. So the lines have different intensities. Mostly they're sort of order unity. So these are relative intensities. If you put the keyword absolute on the line, it will save the intensities of a line either as ergs per second, which is a luminosity, or as ergs per second per square centimeter of cloud surface, which is an intensity. So they're both referred to as absolute cases. We'll talk about luminosity and intensity cases in a later video. This is part of specifying the boundary conditions on the model when you set it up. So these are some predictions for the smoke test for the input deck. So you can see the numbers are tiny numbers. So this is 10 to the minus 25 ergs per, I don't know if it's intensity or luminosity, ergs per probably per square centimeter per second. And different lines you can see have very, very different absolute intensities. The last option is in many ways the most useful if you want to create line ratio diagrams without having to write an external script. So if you'd save linelist ratio, in this case, the input data file, the file that lists the lines, lists them as ordered pairs. So it has to be an even number of lines. And the code will read the first line and divide it by the intensity of the second line. So that would be the Balmer decrement, H alpha to H beta. Here's Lyman alpha H beta, so it would figure this out. Then the O3 to H beta, that's used for many things. This is a very famous temperature indicator. You can measure the kinetic temperature of the gas and a density indicator. So this is in the file line ratio.dat in the helper files for this video. The output looks a little bit wonky because it has a huge label. The first row is always a column label and they're tab delimited. So the first row says this is Lyman alpha divided by H beta, and its value was over 200. Here's 507.03 divided by H beta. And so it goes on and on. So it's a very, very useful facility if you want line ratios, say, to make a BPT diagram. That would be very useful for that. So we're going to go on from here and combine this option with the grid command to generate some interesting plots showing what happens to the spectrum if we change the density or other parameters.